So we have now seen 7.1, which was the atomic physics, point 2, which was the nuclear physics, and now we're going into 7.3, which is the last part of topic 7, and it is particle physics, the structure of matter. So in 1870, Thomson, he had no idea how the atom actually looks like. So he suggested that after doing some experiments, it looks like a plum pudding, as he said. So basically you have a gel, and inside that gel you have positive and negative charges. That's not how an atom is, but that's the best they could do at that moment. Later on in 1910, after doing some experiments, and after sending some alpha particles are helium nuclei, they were sending them with high velocities towards thin gold foil, and they could see that some of those particles were slightly deflected on the gold atoms. However, others they were sent directly backwards, which means that Thomson's model was not right, because clearly there is a very dense area inside the atom. That's the nucleus. They didn't know it back then. And there is also the electron cloud around the nucleus, which causes the alpha particles to be slightly deflected. So therefore they found out that there is something in the core that is positively charged, and there are also electrons around in the form of a cloud. So they were starting to look into the particles that form an atom. That's not the whole story. However, later on they found out a better view for the atom, and they discovered other particles as well. So in 1980 and 1928, we have Dirac that found out the existence of the positron. In 36, Anderson discovered the muon, and so on. And by the end of 1960, physicists had discovered over 300 particles, and there was, of course, a need to classify them. So the classification of particles, that's what we're going to look into today. And this came with the Standard Model. So a Standard Model is a theory that was formulated towards the end of the 20th century, so it is quite recent, and it came through a combination of experimental discoveries and theoretical developments done. Experimental discoveries, as for example the bottom quark in 1977, the discovery of the top quark in 1995, and later on it was also confirmed by the discovery of the Higgs boson in 2012. I was actually at the university at that time. So what is this model? This model says that there are particles that cannot be split into smaller particles. There are particles that make up the matter, and they cannot be split into constituents, because those are basically the building blocks. Those particles we call the elementary or fundamental particles, and they are, as we call them, the leptons. This is one family of particles, quarks, the second family, and the gauge bosons that we're going to look later on. But for now, we are going to focus on leptons and quarks. The leptons are basically those 6 particles that I have written below. The electron, the muon, the tau, and the neutrino of the electron, the neutrino of the muon, and the neutrino of tau. You have seen the electron before. It has a charge of -1, and a very similar particle to the electron, but with a different mass, is the muon. And a similar particle to the electron, but with a different mass, is the tau. All of those 3 have charge of -1. And because of the fact that they belong to the family that we call leptons, that is the lepton number here, they have a lepton number of 1. They are leptons and they're not baryons, so their baryon number is 0. Now, electron, muon, and tau come together with their neutrinos, because in a reaction, whenever you have an electron appearing, as you have noticed by now, when we're doing radioactive decay and so on, it was coming together with a neutrino. This neutrino has zero charge. All of the neutrinos have zero charge, but because of the fact that they are leptons, they have lepton number of 1, baryon number of 0. Now, each particle comes together with the antiparticle. And the antiparticle are particles that have the same mass, but they have opposite Q, L, or B. So different charge, opposite charge, lepton number, and baryon number. So in this case, the electron has an antiparticle we call positron, as you also have seen quite recently. And this has charge of +1, lepton number of -1, and baryon number of 0. The same with anti-muon and anti-tau. Those are the antiparticles. And antiparticles, we like to notate them with a bar on top of them, this way. So you expect that those will also have +1 of charge and a lepton number of -1. Now, neutrinos have their antineutrinos as well, and they have 0 charge, but -1 lepton number and 0 baryon number. We completed now the family of leptons. Congratulations. Let's go and look into the quarks. Quarks, we'll start with the first six that I wrote. U, D, T, B, C, and S. Those are the quarks. And those letters stand for up and down, top and bottom, charm and strange. And those have charges that are a little bit different than what we're used to. For example, the U, the up, has a charge of +2/3. And the down has a charge of -1/3. The top again has a charge of +2/3. The bottom -1/3. +2/3, -1/3. That's how they look like. And now they're not leptons, so their lepton number is 0. However, they have what we call the baryon number. And the baryon number is 1/3 for all of them. All right. Now, as you're expecting, you're right, quarks come with their antiparticles, the antiquarks. And antiquarks, again, now they will have the opposite charge, the opposite baryon number, the opposite lepton number, and so on. So the anti-up has a charge of -2/3, and the anti-down is +1/3. -2/3 +1/3. -2/3 +1/3, as you would imagine. Lepton number is 0. It doesn't change because those are not leptons, but they're baryons. So their baryon number is the same, but with a negative in front, because those are the antiparticles. Good. This was the family of quarks. Now, leptons do not come together to form other particles. However, quarks, they come together to form other particles. So leptons exist on their own. Quarks never exist on their own. But they, and what did I write here? I don't know. They make up hadrons? Yeah, I probably wrote that. And now the hadrons that are made out of quarks, it is another family of particles that is divided into two categories, the mesons and the baryons. The mesons are particles that are made out of two quarks, a quark and an antiquark, and baryons are made out of three quarks, either 3 Qs or 3 anti-Qs. So let's look into the mesons. The mesons, and there is a pion here, there are quarks that are made, they're particles that are made out of two quarks, as I said before, and you can see that the positive pion is made out of U, up, and anti-D. Let's see, if it didn't give us the charge that is +1, would we be able to find it? If you look at the charge of the U, it's +2/3, and for the anti-D is +1/3. So the charge would be +2/3 from the U, +1/3 from the anti-D. That would make us 3/3 or 1. So that is why the electric charge of the positive pion is 1. So even if they don't give us this and they give us the quark content, we can actually find out what is the charge. Now let's look into the baryons. The baryons are made out of 3 quarks. For example, you can see here how you can have the proton made out of UUD. Up, up, and down. That's the 3 quarks that make it. And it has an electric charge of 1. Indeed, if you take the charges of up, up, and down, so you have up is 2/3, plus the other up 2/3, and the down is -1/3. That would give you 3/3, which is 1. That is why the charge of the proton is +1. Now, if you take, for instance, the antiproton, it has anti-up, anti-down, and anti-D quark content. So mesons are made out of 2 quarks. I will write here the pion, the positive pion. So a positive pion is a particle made out of U, the up, and the anti-down quark. Or if we look into the kaon, K minus, it's made out of the strange quark, and it's made out of the anti-up quark. And the proton is made out of 3 because protons are baryons. So it's made out of UUD. And a neutron, you can see here, is made out of UDD. If you add up the charges for the neutron, you will see that the charges of the quarks cancel out. So you're actually getting a 0 charge that the neutron has. So that's a proton. That is an antiproton, or sometimes you can see it notated this way. This is a neutron, and this is an antineutron. So you have anti-up, anti-down, anti-down, and so on. So particles like baryons and mesons consist of quarks. Now, will you have to remember this table with all those numbers by heart? Actually, no. You're given this table here. This is your formula booklet. 7.1, 7.2, 7.3. You're given the table, but you have to get used to the way that this table is given. For instance, it gives you that up, charm, and top have this charge and this baryon number. So you need to know yourself that if you take anti-up, anti-charm, anti-top, this will be negative and the baryon number will be also negative. So in a way, it is given, but you also need some knowledge to understand and know the table. So when you have a reaction, the Q, the charge, the B, the baryon number, and the L, the lepton number, they're always conserved. There is something that we call strangeness, but I will not get you into that yet. Maybe at some point if we meet it in a question. And the thing is that we know of some fundamental forces in nature. So the current theories suggest that there are just 4 fundamental forces in nature. Those are the gravitational force, as you know of, which has infinite range and acts on all particles. There is the electromagnetic force, as you know, which has infinite range but acts only on charged particles. That would be good if I hadn't erased that. There you go. And we have the strong nuclear force, you have also heard of it in nuclear physics, that acts between hadrons. It acts between neutrons and protons. And therefore, that's why we have met it in nuclear physics before. And there's also the weak nuclear force. It's a force of a small range, smaller than the strong, and it acts between quarks and leptons. We'll get to this table again when it becomes relevant. But I have here some reactions, and let's see if those are possible. It says determine whether or not the reactions violate any of the rules that we learned. So we have a muon, it's negatively charged, that basically becomes electron and a photon. So we will look into Q, B, and L, and we will see if those are violated. Let's look into the charge. The charge of the muon is -1, and the charge of the electron is -1. The charge of the photon is 0, so this is good. It's not violated. Now let's look at B, the baryon number. The muon has a baryon number of 0, the electron has a baryon number of 0, and the photon of 0. So that's okay also. Let's look into the lepton number. The lepton number of muon is 1. The lepton number of electron is 1, and the lepton number of gamma of a photon is 0, because gamma is not, photon is not a lepton. So is this reaction possible? Well, the answer is that, yeah, this reaction is fine. So we can say that this reaction does not violate any of the rules. Let's go to the next reaction. You have a proton plus neutron giving you a proton plus a pion. All right. Now, let's look into Q, B, L. Proton has charge of +1, 0 charge the neutron, +1 here, and 0. So there we go. The Q, the charge, is not violated. Let's look into the baryon number. The proton has baryon number of +1, as you will see on the tables above. The neutron has +1, and then the proton has +1 here, but the pion has 0. Because if you look into this table over here, you can see that all mesons have a baryon number of 0, and pion is a meson, is made out of 2 quarks. So in this case, this is violated. When one of those Q or B or L is violated, then the reaction is not possible. The lepton number here, there's nothing wrong with the lepton number, but because of the fact that B is violated, then this reaction is not possible. Here is possible because everything was just fine, everything worked. Let's go to the third reaction. The third reaction says the proton becomes pion positive and pion negative. So a proton becomes pion positive plus pion negative. And first you can see that the charge is violated because it becomes +1 and then -1 is not possible. The B is also violated because the B for the proton is 1. The B for the mesons is 0, so this is also violated. The lepton number is the only thing that is not violated, but this doesn't matter because this reaction is not possible. So, state the name of an exchange particle involved in the weak interaction. I will get to what this means, but this is the way that we're looking into if reactions are not possible or possible. If Q, B, and L are violated, or either of those is violated, then the reaction is not possible. Now, we saw those 4 forces that are the fundamental forces. The thing is that you have Yukawa in 1935. He proposed that The force between a pair of particles is transmitted by particles called gauge bosons. And this is the other family of particles that they are fundamental. So you cannot split them further. They are the building blocks in a way. Well, not the building blocks. And they are exchange particles, as we will see here. So the four fundamental forces have different ranges, as we saw before, and a different boson is responsible for each force. So in order to have a force going on, you need to have the transmission of those gauge bosons, of those particles. The mass of the boson particles establishes the range of the force, and the bosons carry the force between the particles. All those are important things. That's why I wrote them down. So imagine that if you have particle A and particle B, they interact by transmitting those particles that are called gauge bosons. So this is your gauge boson in this case. Right. So the force is taking place through this interaction, through the transmission of this boson. And the thing is that each force out of those four fundamental forces that we saw have different exchange particles. For instance, you can see that for the gravitational force, the exchange particle is graviton. We haven't discovered it yet, that's why it says undiscovered. The weak nuclear force has those three particles, the W plus, W minus, and Z0 bosons. The electromagnetic force carriers are the photons, and the strong nuclear force are the gluons. Okay, so when it says here that the question said, state the name of an exchange particle involved in the weak interaction. Well, as you saw in the weak interaction, there we go. Those are the exchange particles. W plus, W minus, and Z0. That's that. So what else?